The Hokey Pokey Cosmology, the algorithm of reality. In the 1940s, an instructional sequence entered the cultural record. It dictates a precise recursive procedure. Define a system boundary, manipulate a local subsystem across that boundary, agitate it, rotate the structure, and repeat until the observer is fully integrated into the event. To be absolutely clear, this is an accidental structural allegory. The historical record reveals a layered origin of communal rhymes entirely separate from the development of modern physics. There is no evidence its creators intended to encode quantum mechanics, yet the choreography functions as an algorithm. It applies a rigid set of operations to one selected component after another. It distinguishes left from right. It moves parts inward and outward. It demands kinetic disturbance. It executes spatial rotation. These playground instructions map onto the formal grammar through which modern physics describes reality. The structural resemblance is too orderly to ignore. The song's final declaration insists that this procedure is what everything is about. It proposes a cosmology where reality is not a static object waiting to be understood from a distance, but an ongoing activity, a physical participation. Subjecting this childhood ritual to uncompromising physical rigor reveals an unexpectedly serious vocabulary for the universe. The simple distinctions of a playground dance happen to trace the exact fault lines where classical intuition breaks down. The algorithm begins by putting a foot in, but before a foot can enter, a boundary must be defined. The physical floor contains no natural dividing lines. The participants draw a circle, and by doing so, they turn continuous space into a binary choice. This diagram illustrates a core practice in physics, relational ontology. A physicist must isolate a system, such as an atom or a detector, and distinguish it from everything else. The inward or outward status of the system is not an absolute property of the object itself. It is defined entirely relative to this chosen boundary. The alternating motion of a limb moving across a boundary tempts a comparison to quantum superposition. It is easy to imagine the foot occupying two distinct states, inside and outside the circle, at the same time. Direct physical reality is more constrained. A classical foot moving back and forth occupies a standard sequence of separate locations in time. A true quantum state, by contrast, contains mathematical amplitudes for multiple alternatives simultaneously, which can interfere with one another. A human body cannot sustain a macroscopic superposition between the center of the room and the exterior. Physicist Wojciech Zurek's work on environmental decoherence explains why. A dancer is a massive, warm object constantly interacting with air molecules, thermal radiation, and the floor. This dense environmental noise disperses any delicate phase information instantly. The environment effectively monitors the system, forcing stable classical states to emerge. The first step focuses on ontology rather than movement. It demonstrates that meaningful physical states like in and out do not exist until a boundary is drawn to create them. The second step dictates a deliberate repetition. After testing the right appendage, the rule is applied to the left. The choreography treats the mirrored halves of the human body as interchangeable inputs. For much of history, scientists assumed the universe operated the same way. This assumption was called parity conservation, the belief that the fundamental laws of nature would behave identically if all spatial coordinates were reversed, as if viewed in a perfect mirror. In 1956, theoretical physicists Tsung-Dao Lee and Chen-Ning Yang reviewed the available data and pointed out a critical gap. They noted that parity conservation had never actually been tested in the realm of weak nuclear interactions. The following year, an experimental team led by Chen-Sheng Wu designed a highly sensitive test to answer the question, utilizing cobalt-60 nuclei supercooled and aligned within a magnetic field. This model illustrates the expected outcome. If nature was perfectly ambidextrous, the beta decay electrons emitted by the weak interaction would spray symmetrically, respecting the mirror geometry of the setup. The experiment revealed a different reality. The electrons ejected preferentially in the direction opposite to the nuclear spin. Nature failed to replicate the mirror process. The results establish that the weak interaction distinguishes left from right. Gravity and electromagnetism allow a dancer to perform identical motions with either foot, but at the level of the weak force, the universe reveals a handed structure. We do not inhabit a perfectly mirror-symmetric cosmos. Having crossed the boundary and tested spatial symmetry, the algorithm mandates disturbance. The selected component must be rapidly agitated. In standard mechanics, shaking is a rapid change of velocity. It forces energy through joints and tissue, air and floor, and propagates outward, pushing evidence of the movement into the surrounding space. This connects back to the mechanics of decoherence. By vigorously disturbing the subsystem, the environment becomes entangled with countless surrounding degrees of freedom. The room itself physically records the event, cementing the loss of any quantum interference at the macro scale. The participants hear a shared pulse and execute these actions at similar times. This temporal coordination across multiple nervous systems is classical synchronization. It must be stated precisely. A group of people moving in unison is not a macroscopic display of quantum entanglement. Entanglement is a strict mathematical relationship defining how non-local states correlate. It is not triggered by mutual participation at a party. The mandate to shake the system acts as a blunt mechanical lesson in thermodynamics. It guarantees that a localized action cannot remain isolated. The environment always finds out. The fourth operation is a transformation of the observer's frame. The sequence demands a complete 360-degree rotation of the entire system. Classical geometry provides an obvious expectation. A rigid macroscopic object turned exactly one time will return perfectly to its original physical orientation. But quantum spin complicates the geometry of rotation. For half-integer particles known as fermions, the building blocks of matter, the mathematics dictate a different reality. Fermions are described mathematically by a spinor. When a spinor rotates 360 degrees, or 2 pi radians, it acquires a negative phase. As illustrated by the topological belt trick, one complete turn leaves the geometric connections twisted. The state has been altered. To untangle the topology and return the spinor to its original mathematically unaltered state, it must be rotated a full 720 degrees, or 4 pi radians. Laboratory verification of this property arrived in 1975. Neutron interferometry experiments conducted by Helmut Rauch and Samuel Werner demonstrated coherent spinor rotation, proving that nature respects the 4 pi symmetry. A human body governed by classical mechanics faces forward again after one turn. This 720-degree property strictly applies to the phase transformation of isolated quantum states. Yet the choreography points directly at a mathematical property of spinors. It instructs the system to rotate in order to test its spatial symmetry, brushing against a physical law where, at the deepest layer of reality, one full turn is only half the journey. The algorithm operates through strict reductionism, isolating the right foot, the left foot, the hands, but it eventually runs out of discrete components. The final step discards the catalog of parts and commands the whole self to cross the boundary. This escalation triggers a well-known boundary crisis in physics. The external observer, previously manipulating the localized subsystem from the outside, is suddenly forced inside. Mainstream quantum mechanics does not require a conscious human mind to collapse probability into reality. Measurement is a physical interaction establishing a stable record. The universe functions regardless of our awareness. But defining a complex system requires recognizing emergence. An organized whole possesses behaviors, rhythm, memory, and chemical processes that do not exist in a vacuum. You cannot locate a dance by endlessly dividing a dancer into constituent protons. Look at the resulting structure. We have drawn relational boundaries. We have tested spatial asymmetry. We have leaked kinetic information into the environment. We have executed topological rotations. Finally, we have integrated the observer into the closed system. The algorithm's final declaration offers no ultimate noun or object. Meaning is found in the physical execution of the procedure. It suggests that reality is the ongoing process of crossing boundaries, transforming states, and entering the system completely. And that, with all appropriate scientific qualifications and one additional turn for the Fermions, may be what it is all about.